friends from Medical Central and Tech Mahindra and fellow students, it gives me an immense pleasure to introduce among us Professor Sir David Payne. He is a well-known physicist, engineer, and also, I gather, he is also a philosopher. So, he is currently the director of Optoelectronic Research Centre over at University of Southampton, and he is well known globally for his research work in the area of optical fiber communication. It has led to some great impact in the area of telecommunication and laser technology. And he is also a very good friend of our dear colleague Professor Pal. And without much ado, I would like to request Professor Pal to give a short introduction to himself about Professor David Payne's work. And Professor Pal, the floor is yours. Thank you.
Thank you, Niranjan, Professor Dande, dear students, and other dignitaries in the audience. A very hearty welcome once again on behalf of the Mahindra Center. It's just so happened that I know Professor David Payne for almost 40 years now. Wow. For a very long time. We have been also collaborated. So I thought I will share with you some of the important hallmarks of Professor David Payne. So David Payne, whom we often call as Dave, he is known to the professional world as Dave. He is the director of Optoelectronic Research Centre, University of Southampton, for last 18 years. And this is the most famous and well-known Center for Research on Photonics, which is in otherwise some people call as photonics as optoelectronics. They are both synonymous terms. He has been a distinguished research pioneer in fiber optics and photonics for over 43 years. Without abundant and inexpensive optical communication, that he is one of the forefathers which developed. And without this communication facility that we have, we take it as just like anything else. Without this optical communication, we would not have the internet, no Google, no Yahoo, no Facebook, no Amazon, no eBay, and no Flipkart. This is equivalent to Amazon in India. He discovered area fiber amplifier, which is known in short as the EDFA. And because of the discovery, which took place somewhere around 1987, by 1993, the first area fiber amplifier-based transatlantic communication was tested. So from the invention to the product, it was only a period of only about 6 years. Although typically, invention to an actual product of this kind normally takes almost 20 years. So with the discovery of EDFA and the consequential emergence of what is known as the dense wavelength division multiplexing, DWDM in short, you'll get some glimpse of it in stock, has been the enabler and facilitator for this network revolution that we have witnessed. He completed his studentship in power engineering from University of Southampton way back in early 1970s. In one interview, Dave once said that what incredible luck to have got into this field that has changed the world. I am also fortuitously got into this field around the same time, mid-1970s, after my PhD. He is often asked, are you an engineer or a scientist? He replies, to a scientist, I am an engineer. And to an engineer, I am a scientist. I bounce between the two fields. Honors and recognitions are many, so some I will just quickly list here. He was knighted in 2013. Honors list of the Queen for services to the photonics research and applications. So he is now a Sir. He is a fellow of the UK Royal Society, Optical Society of America, which is now known as OSA Optical Society, UK Royal Academy of Engineering, UK IET, Institute of Electronics and Telecommunication, Institute of Physics, UK, Honorary Foreign Member of the Russian Academy of Sciences, Honorary Foreign Member of the Royal Norwegian Academy of Sciences. Incidentally, this Royal Norwegian Academy was established way back in 1760. He is much bigger than me in terms of as a scientist. Fortunately, myself and Dave are the only two foreign honorary members of Royal Norwegian Academy in the area of optical communications. Tyndall Award, which is the highest award in photonics, awarded by IEEE Photonics Society USA and OSA, the Optical Society. He was one of the very first awardees of this. Eventually, he also became chair of the selection committee of that. He is an awardee of the Marconi Prize, very prestigious. There are only, today I learned from him, there are only 40 Marconi Fellows in the world. It's a very selected few. And right now he chairs that particular committee which selects the new Marconi Fellows. He also got the IEEE Photonics Award 2007, UK Rank Prize for Optics, Franklin Laureate USA, Edward Rhine Laureate Europe, Millennium Prize Laureate, which is something equivalent to almost Nobel Prize from Finland, Thomson Reuters Citation Laureate. You know, as a scientist, your contributions are often judged by any award committees that how much citations your papers have got, or cited by other scientists around the world. He is one of the most highly cited researchers with over 650 publications. He is most referenced influential researcher in the field. Mountbatten Medal of IEEE, UK, Kelvin Medal of 8 major engineering institutions in the application of science to engineering. IEEE REC Instant James Clark Lecture Award, which is one of the latest he got in 2014. He is a leading entrepreneur, which is one of our emphases for this particular college. He mentored photonics cluster of 10 to 12 companies around which grew around Southampton University, and most of these were so successful they got bought by very big companies, names in the international, multinational companies like Cisco, Schlumberger from Germany, and so on. Even in his academic research, Dave likes to see something useful at the end of the tunnel. He once commented, "I don't mind if application is for 20 years' time, but I need to know what it is for." I met Dave for the first time in summer of 1976 at NTO, which is now known as, which used to be known as the Norwegian Institute of Technology in Trondheim, as a postdoc fellow. He was invited by my group head, whose name is Shell Loteja, as a consultant to help us in the fabrication art, developing the art of fabrication of low dose high silica optical fibers by a technique known as the MCBD technique, modified chemical vapor deposition technique, under development in our group at that time. We were all amazed by his deep knowledge, deep all-round knowledge in that particular field. After a full working day, consultations with him and his lecture, I still remember we had a dinner reception arranged for him by my host at his home for the entire group. And it started at about 6 p.m. In Norway, it is midnight sun, country of midnight sun, the sun doesn't go down in the summer. So it started at about 6 p.m. I don't know whether they would remember. We actually dispersed from Professor Shell Rotiza's home the next morning 6 a.m. So the dinner was for 12 hours, primarily because we all had a large number of questions to ask Dave in that encounter. He has made significant contributions on many forms of photonics, not only European Gold Fiber amplifier. He will discuss with you in his talk about kilowatt and higher power fiber lasers, which are used for today for welding and many other industrial applications. He is one of the first who has established the field of specialty fibers like spun fibers. There's something you can see there's a name bowtie fibers, very interesting. In recent years, together we have been research partners in a very major project funded by the British government, about 500,000 British pounds, under the UK-India Education Research Initiative scheme. And it so turned out that our project is the showcase project out of over 150 projects funded under this scheme, according to British Council. I met him last in January this year at UNESCO during the opening ceremony of the event declared International Year of Light and Light-Based Technologies, which is represented in this particular website. As you were watching a short film about that, this is the International Year of Light. UN has adopted a resolution in its General Assembly on 20th December 2013, stating that we recognizing the importance of light and light-based technologies in the lives of the citizens of the world and the future development of global society on many fields, it decides to proclaim, UN decides to proclaim 2015 the International Year of Light and Light-based Technologies to increase the awareness among the public of the importance of light science, optics, and light-based technologies. So this lecture is being actually planned as a part of the International Year, our contribution of ABC's contribution to International Year of Light, and it will be actually posted on that particular site very soon after this talk. So the International Year of Light is declared by the UNO, and it was inaugurated on January 19 in Paris. So before I leave the floor to Professor David Payne, I would just like to share with you a quote. The ethereal glow that inspires countless painters, poets, the first part of the electromagnetic spectrum that humans discovered is about to take center stage. It was taken from an article which appeared in Optics and Photonics January issue. With that, I will leave the floor to Professor David Payne to tell you about his association with this field for over last 40 years.
Thank you, Bishnu, for that extremely generous and rather long introduction. But you missed my most important award. For this year, I was fortunate enough to be elected to the 500 most influential people in the United Kingdom. Now, why is this the most important? Because it has David Beckham on it as well. And I've always wanted to be on a list of people with David Beckham on it. But it was also full of very beautiful fashion models, which was nice at the reception. And my other great hobby, some of the great chefs, like Heston Blumenthal in the UK. So it was a fun reception. So I changed this talk today because when I learned about this fabulous new university and realized who my audience was, I thought I should do something a little different. In particular, what I wanted to do was, rather than give you a technical talk, which was my original intention, is to actually give you something which emphasizes the way in which invention and innovation works, using as an example my heroes, and using the example of the global optical internet and optical fibers and how this came about. Because I find this a fascinating story, and it enables me to bring out a few very important things that I have learned in a very seriously long time on the roller coaster of innovation which created today's global internet. So as I said, I changed this completely, so I hope it all works still. So let me start then. I'm going to introduce you to my heroes to start with. So this is Charles Townes, Nobel Prize winner 1964 for the invention of the laser. You'll see why that's important in a minute. Sadly, he passed away just 1 month ago, and you may have caught, it was in all the news, at this great man who was 99 years old when he died and still working. Something to remember. The world has changed, folks. Nobody who's in science and engineering today retires anymore. Plan for a very long working life. Charles Cow, a very old friend of mine, very influential in my career. He got the Nobel Prize for invention of the optical fiber for telecommunications in 2009. And finally, Vint Cerf, who is my co-chair, deputy chairman for the Marconi Society, who won the Queen Elizabeth Prize in 2013 for the invention of TCP/IP protocols, which drive the internet today. Now you'll see why I've chosen these folks as we go through this talk later. So, let me try to put into context, because you know, innovation and invention, when you look back at it, is obvious. But it isn't and wasn't obvious at the time. So if you want to understand invention and innovation, you have to understand the environment in which it emerged. That's why I've chosen this slide. This is a slide which shows August 1858, the inauguration of the Atlantic Telegraph by Queen Victoria and President Buchanan. And it was for 4,260 kilometers using Morse code at less than 1 bit per second. You remember the old Morse code? Well, you won't, you're too young, but some of the older guys in the audience certainly will. And the message that Queen Victoria sent was, "May the Atlantic Telegraph prove to be a bond of perpetual peace and friendship between the kindred nations, and an instrument destined by divine providence to diffuse religion, civilization, liberty and law throughout the world." Now, how many of you young students think that that is true of the internet today? I don't see any hands up. Because it shows a certain naivety, doesn't it? Because actually the internet today brings fantastically good things, but it also brings some bad lands. We're concerned about global security, cybersecurity, criminality, pornography, all of those things. But it showed the need for a global communication medium, which all of you young students take for granted. Of course you've got a mobile phone. That goes, by the way, optically almost every time you use it. Of course you've got an internet which allows you to pull stuff down from the US, from China, wherever else. But it wasn't always that way. So here's an example further about the environment. Anticipating the internet. This is taken from 458 BC. So that's over 2,000 years ago. And this is actually written in a play called Agamemnon. And this play concerns the fall of Troy. Now, Troy, as you can see up here, there, and down here, Athens, and they needed to communicate. So how do you think they did it in those days? They sent a ship, they sent a runner, they sent a horse. Well, watch this. This is what it says in the play. What time of day was it when Troy was destroyed? Clytemnestra, who was the wife of Agamemnon, says, not day but at night, last night in fact. And the news has traveled already? How could that happen? And she replies, at the speed of light. Hephaestus' sacred light blazed from beacon tower to beacon tower, from Ida's top to Lemnos, and from there to Athos, that island sacred to Zeus. where they set the blaze they had kept prepared so long. So what, of course, they were doing, and we plotted this out, by the way, and we did the calculations. That's the route that they used. So there were 1, 2, 3, 4, 5, 6 hops, and each of those was a huge beacon. Now we calculated that the beacons, in order to have visibility over that distance, would be 10 meters high of wood burning, consuming megawatts of heat in order to create a very small amount of light, sufficient to be seen across all those hops from fire to fire to fire. So we concluded the following. It was the first free space optical link transmission over 600 kilometers. The longest span was 150 kilometers, and it was 1 bit per night. Pretty slow stuff. A 5 to 10 meter wood pile of fire, tens of megawatts. Too bad if it rained. Fortunately, in that part of the world, it doesn't rain very much. So you see the point that I'm making here, which is that optics was always the communication medium of preference, and it was waiting to happen, and I'm going to show you why it took so long in a moment. But here's another example, which was the North African so-called Red Indians, who use smoke signals, as we all know, and we have renamed this as the laser. If you can't see that, what that stands for is Light and Smoke Emission Regulation System. Okay, now there's a modern equivalent of that, of course, which we call the iPhone 6 or the iSmoke 5S, which gives you clearer signals, smaller blanket, and longer lasting fire. Okay, but it didn't change things very much, just like the iPhone doesn't. So let's move forward a couple of thousand years, and we look at modern optical communications, because the innovation required for all that to change was the same as you saw in each of those: a transmission source, a modulator, a detector, and a transmission channel. Now, the invention of the laser gave us the source, the optical source. So instead of having to build a 10-meter high pile of wood and burn 10 megawatts of power, I have a laser which gives me sufficient intensity. There's everything that I'd ever needed. A modulator we had, a detector we had, but the transmission channel was the bit that was missing. Remember what it said? Too bad if it rains. So you've got to have a transmission channel which gets you through rain, a pipe of some sort. So here's an interesting patent which was written by Art Charlot, who was the brother-in-law, in fact, of one of those persons that you saw earlier, Charles Townes, inventor of the laser. And he notes that you have a generator, moderator, detector, and modulating source, and they wrote a combination system for operation in the infrared, visible, or ultraviolet regions of the electromagnetic wave spectrum, comprising a monochromatic maser. They hadn't even invented the word laser at that time. A coherent modulated maser amplifier, a modulating source, and a detector. But what they missed was this: the transmission channel in order to get the light to the detector. And another example of the way that this was used in those days, somewhat earlier actually, was the optical telegraph. And here's an example. These are still found all the way around in Western Europe. And this was a French version, very sophisticated, because you see on the top here, it has the first signs of coding. This is a semaphore arms which had different angles so that you could send different codes from beacon to beacon, and that is why throughout Europe you have telegraph hills, because the telegraph is what these were called. So along comes Charlie Cowell, my friend, And you know, we all look back and we say, oh, well, of course optical fibers would work. But remember, once again, the environment. The environment is shown here in the way that I have plotted this particular graph here. And what this is plotting is the known transmission of glass when I was a student. And I plotted it from an extreme range from the deep UV ultraviolet out to 100 microns here. And the reason I've done that is because a lot of people, students in particular, always ask me, well, could we find something better than glass? The answer is, I don't think so. But I'm not saying no. And so this is what I did in order to try to convince myself. And you see, plotted up here is how far you could get through a block of glass of any kind if you had it thick enough. And the answer is that just through this incredible piece of luck, just here in this region just beyond the visible spectrum of light, there is a region in which we could get through about 100 kilometers. Although nobody actually knew that at the time. Because nobody could measure 100 kilometers. They didn't have 100 kilometers thick piece of glass. So along comes Charles Cow, and he writes a paper in which he says, a fiber of glassy material represents a possible practical optical waveguide with important potential as a new form of communication medium. And everybody said, Charlie, you must be joking. In fact, the scientists are a little more polite than that. They say things like, it is our opinion that glass cannot ever be made of sufficient quality for this to happen, which is exactly what our American friends in Bell Labs said to Charlie. But Charlie was an innovator, an inventor first and an innovator second, in which he said, I don't believe you. I will challenge that. And in fact, he went on to measure only in 10 centimeters that you could actually have a loss which would get you across an ocean. That was a tough measurement to make. So what did they do? Next step, along comes, of course, the press office, the famous press office, who put out a press release. Remember, this is before anybody believes that glass could be sufficiently transparent to get across an ocean. And this particular press release is an interesting one because it has two examples in it of a 10 to the 4-fold miscalculation. So here they are. And it says, referring to optical fibers, they have exhibited an information carrying capacity of 1 gigacycle. Now, the engineers amongst you will know there's an error there. It should be gigacycle per second. But today's optical fibers have a capacity of about 10 terahertz. The second one is it is capable of carrying 10 milliwatts of power. I will show you at the end of this talk that today they can carry 10 kilowatts of power. And finally, the best readily available low loss materials have a loss at about 1,000 dBs per kilometer. In other words, enough to get you through about 1 meter. So interesting context here. So why are these guys, including me, who started my PhD at that time, going around saying, no, 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 we can change all that? You know, that takes a lot of courage. If you'd been wrong, you would have been a fool. If you were right, you're a genius. That's the way it works. So here's another unusual plot. This is plotting the loss of glass from the Egyptian times to the Venetian times to this area here, which is when the Germans in the 30s started to make optical cameras for which they needed high quality optical glass. And the famous Otto Schott, Carl Zeiss, names today, which still exist as brands, purified the glass and made it uniform. And this scale up here is a logarithmic scale. So you can see here, this going down to, in this region, 10 to the 3 dBs per kilometer, 1 dB per meter, is about what that press release you saw just said. Now, along comes who? A young, hairy student, me, and his professor says to him, Dave, just make a fiber drawing machine and produce thousands of kilometers of fibers and make them at something like maybe a fraction of a dB per kilometer. Now, as a young student, my mind had not been polluted in the same way as all of the other experts who were saying it couldn't be done. So, as young students, I hope will continue to do, they said, no problem, I will do that. When I think of the arrogance of that. But never mind. Shortly after that, now, it's not just me that did that, right? This was a set of evangelical engineers throughout the world who similarly believed that you could reduce the losses. Some of that I did, others was done elsewhere, and I'll introduce you to one or two of my other heroes who brought the losses down to a point where you could get through 100 kilometers using silica, and these are the people that did it. You see here the original paper from Charles Cow, Maurer, Keck and Schultz here. And this one is a bit of a cheat because we actually did it first, but our publicity machine isn't as good. And NTT down here at 0.2 dBs per kilometer. So, everything's great. How do you get across an ocean? Oceans tend to be more than 100 kilometers. So, one further problem that needed solving, which is that we didn't have an amplifier, right? Because, of course, you now had a link of low-loss optical fibers, which would come through here, and then had to be detected, decoded, passed across to a new transmitter, and retransmitted as an optical signal. And this was a little bit like a toll gate on a motorway. It slowed everything up. So, actually what was used was electronic amplifiers, but as you know, electronic amplifiers do not particularly have a very broad bandwidth, and they also will scramble up different colors, and I'll tell you why that's important in a moment.
The team at Southampton University's Optoelectronic Research Centre played a pivotal role in the development of optical fibres that underpin the Internet. Even then, the ORC had an enviable reputation for producing low-loss fibre, capable of carrying signals across great distances.
We thought, well, there is a problem here. Optical telecommunications works very well, but only for about 100 kilometers, even with the very best fibers that we had made. The light just dimmed. And what do you do? Because that wasn't far enough to get across an ocean. So we turned our thoughts to how we might change that. Now we were part of a laser group here as well. So you had fibers and lasers together in one group. And we thought, why not combine them? Why don't we make a laser or an amplifier in a fiber itself? So, we thought of this idea and we put erbium into the core of the fiber. Pumped it with a little laser diode, same as you have in your DVD player, and bingo. In 1987 we announced to an amazed world that we'd made an amplifier in the fiber itself.
At the time, in 1987, this was viewed as blue skies research.
It changed the world when it came to telecommunications, and here it is changing the world again in industrial processing, manufacturing, cutting, welding, making holes in jet engines. An amazing variety of different manufacturing techniques.
All right. So, we invented the erbium-doped fiber amplifier, which, as Bishnu has said, enabled the entire internet. I'll show you why in a moment. But here's another interesting piece of innovation. Did we understand, when we started work on this, what impact it would have? And the answer is no, we did not. In fact, from 1985, we had presented work at ECOC in Venice saying the broad fluorescent line width of rare earth ions in glass allows the construction of broadband amplifiers for use in wavelength division multiplexing. Notice the present tense, allows. It didn't exist at the time, but we were using the present tense. It's not will. We published 24 publications, 24 erbium-doped fiber publications as a laser, not an amplifier. Now, those of you that know the physics will understand that actually a laser is more complicated than an amplifier because it has to have feedback. So you take the feedback, the mirror's off, and you've got the amplifier, and we didn't do that until 1987. Why did it take 2 years to take the mirrors off the end? The answer was because we didn't know what we were looking for, right? But here's another observation, which we also at the same time said, as a high-power amplifier, the fiber device could have advantages over the bulk glass systems by reducing the problems of thermal distortion and thermal fracture in 1986. And that turned out to be incredibly prescient because it was the basis of today's favored high-power amplifier. Let me introduce you to Isaac Newton by means of introducing wavelength division multiplexing, because the concept that light consists of multiple wavelengths was first understood and developed by Isaac Newton as shown in this. This is his original sketch. And you see here a light source, which was the sun. He made a hole in the blind, a lens, a prism, which is a dispersive device, and then he observed the different colors of the rainbow here. And he came to the conclusion that light was composed of multiple colors or different wavelengths. And today we call this, in telecommunications, wavelength division multiplexing. So this is how it works. You take multiple colors at the input. Here, they're all in the infrared actually, but I'll call them colors. I've shown 16. We divide them through little lasers. We combine them with today's equivalent of a prism. Together like that, we send them down the fibers. Here's their amplifiers. And then we get to the other end. We combine them together again, split them back out, and we end up with all our channels. And they don't mix. That's why the amplifier made such a huge difference. Because an electronic amplifier would mix them all up. But the optical amplifier allows each of those colors, just like wireless. You know, when you spin the dial on your radio and you pick up different channels, that's because they're at different frequencies. And they don't mix together in the air. Equally, if you send a light signal down a chunk of glass, if you're careful, they don't mix. And therefore, you can spin the dial and you can pick up each of these colors. Now, when it gets to you on your computer, it's already all been done, way down the path. And they're just sending you, possibly in the final drop, either through microwaves in your phone, or as a final drop. Not many people have fiber to the home anywhere in the world. Final drop might be coax, twisted pair, or whatever. Okay. So that's an optical amplifier. So you see where it ended up. That was an optical fiber cable crossing the Atlantic, and there's enough fiber today deployed to encircle the Earth 30,000 times. So that's the story of the optical internet, and you know, the extraordinary thing is that looking at two great innovators, Marconi, who has a similar influence on your mobile phone and the wireless that drives it, to bridge the digital divide, providing accessible global communications, in particular to the southern hemisphere, which if you look at the map, you will discover contains almost no internet services. And Africa, which is where I was brought up, in this place just here, there. In Zambia, has just got internet through this festoon of fibers which has been installed around Africa as an undersea cable. So the phases of the global optical internet, let me review with you. Charles Townes here, and another Charles Cow, who brought us the laser and the optical fiber respectively. Here are these guys, Keckmar and Schultz, who did some of the fundamental and earliest demonstrations of low-loss silica fiber, stimulated by what Charles Cow had done. And these guys here, Emmanuel de Severe, Randy Giles and myself, for the optical amplifier. And this led us to where we are today, 150 million kilometers, 50 terahertz per single fiber, enough for 25 million broadband channels per fiber. So you're all saying, great, this is terrific. What happens next? Everything's fine. Let's talk about creativity a little bit, because these are some of the most creative people in the world. You know, creativity is a linear process. In other words, it builds on other people work until somebody comes along and disrupts it. So I plotted this a little bit for the global internet in optics. So we start with telecoms, we get to the laser, we get to the fiber, we get to the amplifier, we get to WDM, that's that idea of using different colors of light to maximize the bandwidth, and what comes next, because that's where we are today. So each of these great changes has to lead to something new every time we get to saturate the technology. So remember, I've shown you some examples of the Greeks. That wasn't going to go very far. It was good enough for the day. The semaphore that followed from that, the Aldis lamp, the telegraph. And then we start to get wireless, and finally we get to the optical internet. So we have to ask, what's next? So everybody is saying, well, fine. Do we need a next? And the answer is, damn right we do. So here is the growth of the global internet, plotting up here terabytes average per day being transmitted globally against a number of years, and you can see it's going up at a pretty scary rate. And here's some interesting numbers from Eric Schmidt, CEO of Google. Every passing month, more video footage is uploaded to the web than all three big US networks have broadcast in the last 60 years. In 2016, the gigabyte equivalent of all movies ever made will cross global IP internets every 3 minutes. 38 million DVDs per hour. So what are you guys watching? My kids are watching 3 movies at once, I reckon. So, video exceeded half the global consumer internet traffic in December 2011. It's all about video. And it's getting better or worse, depending on whether you're a communications engineer or not. We now have 4K video. 16K is on the way. We have the Internet of Things, which is going to use a huge amount of video. So this growth will continue. There is no question about it. So we're running out of capacity. And what next? Well, here's another Southampton invention I'm going to introduce you to, from Philip Russell when he was with us, which is the idea that you might use a lattice of holes and you might actually have a hole in the middle and use air, not glass. So maybe the Greeks were right, but this is like an air pipe that will carry light. And the reason it carries light is because of this clever structure around here, which is called a photonic band gap, which has to be very, very carefully designed, which has the kind of resonant effect, just like a Bragg grating does, of reflecting light back in. So typically less than 1% of the light travels in the glass, and consequently you get much lower loss. So here's some examples of actual fibers that we've made. Remember, this fiber is about the thickness of your hair from here to here. So incredible that you can make this kind of structure within the fiber to ultra high precision. So let's watch that for the future. And we are now up to 10 kilometers with losses not yet as low as the lowest loss fiber, but in the stabbing distance of current fibers. We're at about 2 to 3 dBs per kilometer now, incredibly in this amazing structure. But I want to talk a bit more about creativity with fibers and introduce you in the last part of this talk to another idea that what we did was, the other thing that drives creativity is stress. And if you are a bunch of very smart guys and things are suddenly going very, very bad for you, you tend to be stimulated to be even more creative. And that stress for those of us working in telecommunication was the boom and bust of the .com. And many of you who've lived through it, it was a pretty tough time. I'd started up a company at that time, and guess what? There wasn't a market anymore because all the telecommunications engineers got fired, growth stopped, and it was a pretty bad time. Fortunately, it's come roaring back again, as we all predicted it would. But sometimes the other thing that I learned is things go in cycles. The key thing in your life is to align with the cycles, folks. If you're out of phase, you're in big trouble. So we decided that we needed to do something different, as did a number of other people. So we went back to our roots, which was lasers. And let me introduce you then to some more heroes. Theodore Maiman, the first working laser in 1960. Eli Snitzer, who demonstrated the first fiber laser in 1964 by taking, before even Charles Cowell, by just taking some very poor quality fiber, doping it with neodymium and wrapping it around a flash lamp. And it worked. Charles Cowell, who we've introduced you to, and these guys for the fiber amplifier that I've also introduced you to. And this then led us to the high power fiber laser. And that has been, and you know something guys, I think that is going to be even bigger eventually than the optical amplifier was. And I'll show you towards the end of the talk why I think that. Now I want you to look at that cut. As you notice that it's not very clean.
But you're forgetting one thing. The materials are impossible to replace. I trust you with the process.
But he knows what I know.
You know nothing, Mr. Bond.
Operation Grand Slam, for instance.
So this is a fiber laser. So my point here is that the James Bond movie was just science fiction, but the reality is today, because of the fiber laser, you can do that. And that was a fiber laser, and you saw in real time making the holes in the next one. So that same fiber laser that is that powers the internet as the amplifier is now taking over all of the commercial lasers for cutting, welding, making holes, drilling, because it is so simple. And it's just a piece of fiber that has within it some rare earth doping. Typically we use ytterbium, but it also can operate at multiple wavelengths by changing the dopant. So exactly the same as we did for putting amplifiers under the ocean, we are now using at much higher power levels for cutting and welding. But I wanted to leave you with some really crazy ideas, because I hope I've taken you through a journey of showing that how at each moment in time, each of these ideas was radical, innovative, creative, and crazy. So I want to stand where we are today, which is what you've seen, this cutting and welding, and asking, let's be crazy and think of what we could do with this technology and try to think forward. So first thing that I would observe, here's my examples of being creative. What is different about your invention? And how does that lead to break conventional thinking? Well, the first thing about them is they're incredibly efficient. So wall plug efficiencies can be 50%, which compared to other lasers, I mean, for example, the carbon dioxide laser, which is used for welding cars, also is about 10%. So huge savings can be made. But the second thing is it's dirt cheap, because you can pull it on a fiber drawing machine and make fiber for almost nothing. And the third thing is it's all solid state. There are no horrible gases, it's very lightweight, it's very robust. So this leads you to say, well, why don't I just connect together in parallel 1 million of them? Because I can then beam combine these, because I'm good at being able to work with fields and waves, because I studied electromagnetic theory at university, and I know that you can combine things together so long as you maintain them in phase. So you put all this lot together and say, okay, so I could have 1 million lasers for the first time, and I could put them together in this robust thing, and I could combine the beams together in this way, which is this is a bit like the internet all over again, right? So we start with a little laser here, we go multiple amplifiers, split it out, and then what's called a phased array of 1 million lasers all together, emitting like a radar or microwave antenna, which is steerable because you can change the phase, and also has built-in adaptive optics, just as the big telescopes do of today. And so you say, well, and where does this lead me to? So in 2002, we proposed this to DARPA, the American Defense Organization, and they said, you're completely mad, you'll never do this. So we got some money off them, and we did it. And we discovered that so long as we matched the lengths of the fibers reasonably to within 10 centimeters, we could get 1.4 kilowatts out of each one. whilst maintaining them coherent so that they could be combined together. At which point our funding was removed. So here's another little lesson I learned: never be too successful, because they take the money away. So who might be interested in this kind of technology? Remember, I've got 1 million fiber lasers, I've got a 10 megawatt capability. You might think weapons, mass destruction, right? Okay. Well, this is a real project. It was funded by the Bill Gates Foundation, and I thought you'd like to see what this actually might do. Now, this is real, right? You can shoot mosquitoes out of the air with quite low power lasers. So here's what the world might look like.
Are you through with mosquitoes? Are you fed up with mosquito bites? Are you tired of going hunting in the middle of the night? The Grumman Brothers present the Star Wars Mosquito Defense System, a unique system which destroys mosquitoes with a laser beam before they land on your skin. All you need is a base station, the laser gun with ultra-ray laser system, and the 4 mirror satellites which you can mount to the wall. The system is very easy to install. First, mount the mirror satellites to the wall. Put the base station anywhere you like, on a table or on the cupboards. Once you activate the main station, the system works automatically. The main station detects the mosquito and sends a signal to the laser gun. The laser gun fires the laser beam, which overrides the mosquito via the mirror satellites. The mosquito is now in the red circle. Watch carefully. The Star Wars Mosquito Defense System does its job while you read the paper in your garden. Because of the 4 co-operating satellites, there is no spot at all where the mosquito is safe. The Star Wars Mosquito Defense System does work safe and effectively. But not only mosquitoes and other insects can be destroyed this way. With the easy controllable object tracking system, you can adjust the system to destroy all irritating elements in your surroundings. For instance, the neighbor's pet. Or the neighbor's house.
Well, you know, once again, like that James Bond movie picture, there's an awful lot of truth in that little video. And I believe that in the not too distant future, you will be able to buy high power lasers for trimming trees, for example. And the costs are coming down all the time. That's a scary prospect, right? So let me continue then, though, with this concept. And where does this take us, as the future might look, with massively high-powered, relatively low-cost lasers? Well, one of the most exciting things about lasers is that they are the only way that you can create the densities of energy that were present at the formation of the interface of the universe. And that's really exciting, right? Because you can easily create conditions which are greater than the energy density of the sun, and sufficient, they tell me, to even boil a vacuum, meaning that if you fire these incredibly high power lasers into a vacuum, you can actually break down vacuum and create particles just as occurred, we believe, at the formation of the universe. And you can make accelerators, such as CERN, by using lasers through a process which is called laser wake field, where you surf particles across a plasma wave which has been created by ultra-short pulsed lasers firing through long plasmas. And it is calculated that using laser wake field, you could make the equivalent of a CERN accelerator in about 100 meters. And maybe in the future, you could even make it on a tabletop. And where would that lead us? It leads us to things like cheap nuclear fuel transmutation, meaning that you can potentially reduce the radioactive life from thousands, hundreds of thousands of years down to a few years for spent nuclear fuel. You can think of tabletop synchrotrons, neutron sources for medical purposes, and so on. So, what might that look like?
And so I can search for what lies beyond the Higgs boson beginnings. The most powerful laser ever conceived is switched on. This scenario belongs in the future, yet the research required to try and make it happen has already started. But exactly what is, I can't.
Existing huge laser experiments fire sometimes only 4 times a day. We're now talking about the possibility that you could do this with an average power so that it's all the time.
The reason this is possible is because of the unique way the laser is conceived.
What happens is you start with a single C laser and then you split that into 8 different channels, amplify, split those channels into 80, split those channels into 80 until you get up to, say, 512 amplifiers. And then those 512 amplifiers, the beams have to be synchronized and brought together to make a single beam.
So this is a joint project that we have with the Institut d'Optique in France, the Optoelectronic Research Centre and the Fraunhofer Centre in Jena, and with CERN involved as well. And if you think that's sufficiently creative, recently my friend Gérard Mourou at the Institut of Optique in Paris has come up with an even more interesting application for these ultra-high power lasers which are enabled by this fiber concept. It's the removal of space junk, which is very, very hard if the pieces are small because they travel at 10 times the speed of a bullet. So, do you think that's sufficiently creative? Do you think that's what's going to happen in the future? Because this won't happen for 30 years, right? Maybe longer. But it currently appears to be the only way that you could remove small pieces of space junk, which are a serious threat up there, and it's getting worse every day. So, that's just a small part of my vision for the future. And you, students, are the people that will make that happen, because I guess Vishnu and I might be retired by the time that this actually happens. But I'm planning on being around to watch it. So I wanted to finish my talk, because I've come to the end of my time, and try to share with you some thoughts about creativity. After 45 years in photonics, being around some of the most creative people in the world. And it's been very, very exciting for me. And so I wanted to share some of those thoughts with you. So the first one is, the older you get, the better I was. Right? How to be successful, because I get asked this a lot. Succeed in spite of management. You know, this, every time I give that slide, you can see the management in the audience looking at me, you know, thinking, who is this guy? Subversive. Yes, I am subversive. Just like C.V. Raman was, who's famous for it. What I mean by this is, it's the purpose of management to create perfectly, smoothly running operations like this one. But what management has to learn is that disruption and creativity is not about smoothness. It's about bursting out of it. It's about creating a huge disruptive spike in the midst of this smooth operation. And it means changing the world, and you don't do that by having wonderful, efficient operations. We need those, of course we do, but you also need to find ways in which you will allow people to break out of that. Because, you know, almost every single creative person has been blocked and told that it would never work. It's just as I was, and just as Charlie was. Rome did not create a great empire by having meetings. They did it by killing all those who opposed them. If at first you don't succeed, destroy all evidence that you tried. Guys, this is the way the world really works. Yeah, of course it works this way, or at least it should. But have the courage to make it work this way. Empower young minds before they become polluted. I've told you this throughout this talk. You young people are our future. We are teaching you, but we are also polluting you. Not deliberately, because we're doing our best, we older guys. But we are in some senses limiting your thinking to our ways. And you have to learn to be critical and subversive in order to become great innovators, creators of the future. So here's my laws of the initial maximum, because a lot of people ask me this about, you know, how do you spot something that's good out of the million things that you try? So the first thing is you have to try. Try first, try often, and learn from your mistakes. Because you're trying, you're going to find something. If you're not trying, you won't. It's simple as that. A successful experiment is worth 1,000 theories. Guys, come on, you know. It's no good just having theories. It's when you see the unexpected in the lab that you come rushing out and say, look what I just made. You can always make your lucky breaks look calculated afterwards, guys. Now, come on, we all do that. Wow, we got lucky. So we write a theoretical paper saying, we knew it was going to happen all the time. And finally, PowerPoint does not create things. Never be afraid to be wrong, or to admit it when you are. The only mistakes to be ashamed of are those where you should have known better and you say to yourself, oh, you idiot. Revisit your apparent failures often. Successful inventions require the right timing. We had this discussion over lunch. You know, if you try to invent an optical fiber technology before the laser, you would have failed. So you needed to be in the right time frame. And that's very important because it means that you might have ideas that look really good, and then you discover they don't work, you forget about them. 20 years later, go back. Ask what's changed in the world that might make it happen now. People are everything. Be bold, recruit the best. You cannot make the world different if you're surrounded by indifferent people. You know, it's amazing how many senior people don't want to work with smart people because they might show them up. My strategy is work with people smarter than you are, right? Take calculated risks. This one I like. It's from India, as you can see. Marry a tolerant partner, right? Here is Vanessa, my wife. And she's just the most tolerant person on the planet. And, you know, she's supposed to be with me here, but at the last minute we had to cancel. 4th time in a row. She's still married to me. I don't know why. But, you know, it's getting very expensive because every time I let her down, I have to buy her a handbag. And so actually on this trip, after I leave here, I go to Atlanta and then to do some business, and then we're going to Mexico together, so she's happy, waiting for me at home. And here she is at the launch of the famous SPI lasers that I told you about, and I discovered another of life's great secrets. A pretty woman can sell anything. And she was selling all our equipment on the stand. She's not a scientist. Whatever. And, you know, be lucky with your friends. So I've introduced you to many of the great people in my field. So here is Vanessa and I with Charles Cow. Here is, this I believe is the first time they ever met, Charles Cow and Charles Townes. And this is, here is Gwen, who is Charles Townes' wife. This is Gérard Mourou, who I also introduce you to. And this is Cindy de Severe, and 2 ladies here. I introduced you to Emmanuel de Severe, who developed the optical amplifier after the initial publications from Southampton. And this is Kathleen Mayman, because she is the wife of Ted Mayman, who was the first demonstrator of the practical laser. So, amazing set of people. Why are the 2 ladies there? Well, Cindy's prettier than Emmanuel, so it's a pretty good one. And Kathleen, of course, now travels the world because Ted Mayman sadly passed away, and she tells his story for him. That's dedication. So, I finish with the obvious observation, I hope. Technology is fun. And here is a quote from a famous Indian, Dhirubhai Ambani, a famous industrialist here. Think big, think fast. Ideas are no one's monopoly. So thank you for listening.
Thank you, sir, for this great lecture. It's been a great learning experience for one of us who are from a different background, but the way you pitched it, we all of us understood. More importantly, from the perspective of the student, I can say that it's been a great learning experience. Thank you very much, sir. A big round of applause for the Now, may I request our founding director, Professor Sanjay Bhandle, to give a small memento as a token of our aspiration to Dr. David Payne.
Thank you very much. Wonderful.
Thank you. Good. What is it?
You have to open and see.
I have to open it. Oh, well. Okay. This is beautiful. This is a deliberate challenge, you know? Oh, wow. So this is it's a little clock, and an amazing pen.
Yeah.
So, thank you so much. It's very kind of you.
Thank you, and we hope to be in touch with you. If you can be associated with the college, we will be honored.
Thank you. Thank you so much.
Thank you.
Right.
Sir, before we let you go, can we have some questions from the audience?
Sure.
One or two questions. Students, if any one of you have any questions, this is a great moment for each one of us to listen to Professor Payne.
Now, I would like to point out to the students here that I had a number of things which I suggested that you do, and you are failing me already. No questions. You are the creative people of the future. You must have questions, because I promised you, remember, that you should always question your superior guys. Don't let us get away with it. So, come on, who's first? Over there?
I'm not a student, but I am one of the best students here. I learn the French language, I learn electronics, I sit in those classes and I learn a lot of maths. So am I permitted to ask a question, sir? Thank you for your talk, sir. My name is Obiji Bhattacharya. On at least two occasions during your presentation, one was about the density of the universe, something another was about removal of the space debris. You did mention that this is the only way that is possible. Unfortunately, my students don't think so, sir. My students will find ways, different, other ways to do so, sir. You have a comment?
A very good point, and thank you for that. A very good challenge. So that forces me onto the back foot to say that I did point out that it was the small pieces. Those are the tough ones. But maybe your students will actually find a way to do even the small ones. The big ones you can get, you can send up a space station, you can catch them in a big net. Not easy when it's traveling at 20,000 miles per second. But, you know, sorry, 20,000 miles per hour. Yeah, I mean, you could be right, and I hope you are right. So this is an example of a challenge. So, who's next? Come on, it's got to be a student. So let me ask one, there's one brave student. Good, this guy's going to pass.
Yeah, my name is Nilan Babu, I'm a student of civil engineering. So I was just thinking, considering all the advances we have in nanotechnology, and you spoke about developing a big enough laser to eliminate space debris, how can we send a small enough laser into our body which will actually kill, you know, the external viruses or disease-causing agents or cancer or what? I mean, in a medical or in a very small way, can we actually develop a laser which is small enough or something?
Excellent question. So, remember what I described to you. We have lasers and we have ways of transmitting them. Remember Charles Townes for the laser, Charles Cow for the ways of transmitting them. So what that says is I could build a big laser, but I could transmit it with a very small fiber. So yes, you're right, and in fact it is done today. There are a number of medical procedures which put a tiny fiber in a probe or a catheter, as they call it, into the human body, sometimes along the veins or arteries, and perform medical procedures. And there are various ways that they can selectively target things like cancers. So it's happening already. because of those two inventions. So I'm not in the medical field. There's probably people here that are better qualified than I am to think of future applications for light in the biomedical field. And it's been used for dentistry, for example, because as you will know, if you get a carie in your tooth, it's a different color, right? So you can blow it out with the laser. There are many applications like that, so very good point, and thank you for that question.
Yeah, and one more thing. It's like, will lasers be economical enough to, say, apply in agriculture or related applications in the future?
Well, let's do that some then. Currently, the breakdown of the cost of a fiber laser, because my company sells them, is roughly 1/3 to a half to buy the diode pumps, which are put into the fibers to pump the laser. And the rest of it is the componentry and the boxes and the electronics and all that stuff. Now the diodes, if we take the diode price, multiply it by 2, we get approximately the selling price per watt. Now currently diodes are selling at about $10 to $15 fully packaged per watt. So let's call that $20 per watt. Lasers get interesting for cutting, welding, and so on at about a kilowatt. So that says it's going to cost $20,000 US today, right? Which is not far off the commercial prices that we have. What could we project forward? Well, I've seen projections which suggest you could get down to about $1 per watt in massive volumes. So now we're talking about $1,000 for a kilowatt, which kind of feels right as a consumer product. If anybody thinks a kilowatt laser is a consumer product, or maybe it will be, then those are kind of numbers. Now, if you want to make a megawatt, so that's $1 million. Now, a megawatt laser at $1 million is, trust me, extremely cheap by comparison with alternative techniques for doing what they will do. So if you look at the defense guys, they don't get anything for $1 million. That's peanuts for them. So if you believe what I'm saying, $1 million for a megawatt laser makes a huge number of things very possible.
Thank you, sir.
Going from the micro to the macro level, Professor, would it be possible in the long run to forestall the threat of asteroids or meteors hitting the planet by sending out laser guns on spaceships to destroy them in anticipation in advance?
Yeah, now that's interesting, because I thought the same thing myself. So I went away and asked one of my colleagues to do the numbers, and we concluded the answer is no. Not because it's not possible, it is actually possible, but one of the things that we need to understand with any technology is that never try to beat really cheap ways of doing things. And we worked out that it would be far, far cheaper to land an atomic weapon onto the incoming satellite or asteroid. We've seen that done just recently, right? And it's far cheaper and far more power to do it that way. So here am I, an evangelist for optics, saying, no, do it another way, guys. It's cheaper. But I was interested to see recently that the Americans have announced a ground-based tracking station using microwaves capable, they said, of plotting dime-sized pieces of space junk whizzing around the world. So the tracking and plotting side seems to be coming along. So now we need the weapons that are able to deal with it. But your point about incoming asteroids is interesting, because I thought exactly the same thing, so thank you for that.
On a lighter note, how to improve the performance of the English cricket team using lasers?
No, the English cricket team are beyond all help, right? But as you've seen, some very clever technology that's, I mean, it's not helping them, clearly, but actually, you know, the concept of using optics and photonics and tracking in sports science is very important. So, you know, we've seen all these tracking the ball as it goes through, all too often missed by the English batsman. We see how far he missed it by. And in tennis, you know, we've seen the line tracking. It's very, very important stuff. So, yeah, maybe we could accelerate the ball from the bowlers through the air. Thank you.
One last question.
Good evening, sir. I'm Sohail. As you said, there's a great development in the communication field. And further, the next step is the holograms, which the many companies are working on. Could you just tell how these lasers are related to the holograms?
Sure. Holograms have been around since Gabor, another great British invention. And of course, they need coherent light. Well, actually, that's not true anymore, but the best holograms are made with coherent light. There are incoherent holograms around. So that's a technology which relies on light sources, which we primarily have already. But I think your question was relating to something that I'm still scratching my head around, which is there some way of using optical communications to transmit holograms and maybe have 3D images transmitted through the fibers? And there are some quite interesting ideas that are just beginning to start up. For example, sending an image, not by coding it digitally into signals and sending the signals, but taking the properties of the image itself directly as light and encoding that onto the modes of a multimode optical fiber, transmitting it in those modes, and then taking it out again as an image. And you might be able to do that with a hologram as well. So this is today's technology. We're all scratching our head and trying to figure out what we should do next. But yeah, maybe that's coming.
Okay, I'm sure there may be some more question. We are going to have Sir with us just outside this thing over high tea. You can always ask him any further question if you have. Before I end this seminar, I would like to thank Mr. Praveen Raj and Mr. Sudhakar Reddy for arranging for the logistic. Special thank to Professor Hariharan Varun and his team for providing us the audio and video support. Thank you all of you for making this to this presentation. Please join us for the high tea. Thank you very much.
Thank you.